In this video, we will be continuing our discussion on hypothesis testing for at most two groups. So far we have been talking about hypothesis testing using the t-test. Okay, so the t-test is used to hypothesize between the population means of two groups at most. And then we have the z-test, which is also used similarly but for significantly greater number of samples. So we might have remembered that this is how our hypotheses looked like. Okay, so we had our null hypothesis for testing means, the equality of means. So here we have the equality symbols. But notice here in the middle, you may also have a null hypothesis that states that your population mean is equal to a certain value that you believe it to be equal to. Okay, that can also be a null hypothesis. In the alternative hypothesis here in the bottom, we have various expressions of inequalities. We have here less than symbols. We can also have a greater than symbol. And these two, of course, are defined by a one-tailed test, okay, because of the less than symbol. But this last alternative hypothesis here, because the symbol of inequality is inequality itself, then this is a two-tailed test. So far we have been assuming when we performed the t-test in Microsoft Excel, if you can remember that, we have been assuming that the variances of the two populations that we were testing were the same. Okay, we were assuming. But it's logical to say that that is not a safe thing to do when we assume all the time that the variances of the populations that we are testing are equal. In fact, we can make a whole new hypothesis about those variances. We may have another null hypothesis stating that the variance of population 1 is equal to the variance of population 2. And then an alternative hypothesis stating that the variances of the two populations are not equal. Okay, so these two populations came from two normally distributed populations. Okay, two normally distributed populations, but this time we are testing a hypothesis with regards to the equality of their variances instead of their means. So as you might have already predicted, our t-test that we have been using to test the equality of means cannot be used in this particular hypothesis testing when we are dealing with variances. And if we are dealing with population variances which are impossible to come by, our only basis as estimates of these variances will be the sample variances, as you can see here. So, how do we test if indeed two population variances are equal? Well, two things might come to mind. First, why not get the differences between them? Okay? The lesser the difference between them, the more equal they are, or the closer to equal they are. But you know, there's a problem with differences, because differences can be positive or negative. Okay? And you cannot just assume absolute values of these differences all the time. So, we are going to resort instead onto a test of their ratio. Okay, the ratio between the sample variances, not the differences. And what you might have already guessed, the closer the two variances are to each other, the ratio between them is going to be closer to 1. And the farther they are from each other, the ratio is going to be farther also from 1. So we are going to be rejecting our null hypothesis here if this ratio is too large or too small. As I mentioned, if it's too far away from 1. And we are going to accept our null hypothesis if this ratio is neither too large nor too small, aka close to 1. In fact, when the ratio is exactly 1, that means that both variances, or that the two variances are equal. Okay? And of course, we are going to accept our null hypothesis here. So these ratio of variances now follow what we call as the F distribution. Similar to the T and the chi-square distribution, this one is defined by a degree of freedom. But take note, in order to get the F value, we had to divide two variances, sample variances. And sample variances have their own degrees of freedom. Do you remember that? At their numerators, we have a n minus 1s. Okay? So, this F distribution, therefore, is not only defined by one degree of freedom, but two. One from the numerator and one from the denominator, because we are dividing variances, sample variances here. And just like the chi-square distribution, the F distribution shows values that are all positive. And the F distribution is going to be most likely skewed to the right as well, just like your chi-square distribution. Okay? This notation that we see here, F sub 1 sub 6, means that the numerator's degree of freedom is 1, and the denominator's degree of freedom is 6. So meaning to say, the original number of samples for your numerator here was 2, and for the denominator was 7. Same as this F distribution here, with 5 samples from the numerator and 7 samples from the denominator. Okay, the greater the number of samples that we have, or the greater the degree of freedom, the more normal your F distribution will look like. So as you can see here, the differences, the first one with 1 degree of freedom in the numerator is very, very skewed to the right. But the second one with 4 degree of freedom for the numerator is now somehow less skewed. I think you can answer this now. Why are there no negative values? Okay, because first and foremost, the F distribution is derived from variances, and there are no negative variances. So just like our T and chi-square distributions, we can derive a particular percentile for any F distribution. Okay? And this percentile of an F distribution with degree of freedom 1 and 2 respectively is everything to the left of this boundary line that we have here. So that's the percentile. So if we are asked to find the 95th percentile of an F distribution with 2 and 4 degrees of freedom, we can use table number 8 at the appendix of the book. Okay? So the vertical columns, or the columns here, represent the degree of freedom for the denominator. Okay? And in our example, or in our question here, that's 4. So we go to the 4th degree of freedom. And the rows here determine the degree of freedom of the numerator, or D sub 1. So we go to 2, because that's what our problem is, 2 degrees of freedom. And the F value here, therefore, is that intersection between the two, which is 6.94. So if we're going to draw this F distribution, we can have something like this, with 6.94, somewhere here. So this is 6.94. And this is 95%. Okay, everything to the left of that is 95%. Now, you might have noticed there are no lower percentages here. These are all upper percentages. So we might arrive at a problem or come at a problem when we are looking for lower percentages. Okay, so what if we are asked, instead of the 95th percentile, to find the 5th percentile? Luckily, we have a relationship between these two. Okay, so we simply have to get the reciprocal of this particular F value. But take note, instead of the P percentile, we are getting now the 1 minus P percentile. Okay? So instead of F and then 2, 4 degrees of freedom and then 0.05 percentile that we see here, 5%, we are now to get the F value with 2 and 4 degrees of freedom and 1 minus 5% or 0.95th, okay, or 95% percentile, and the reciprocal of that. So there is a numerator of 1. So all we have to do is to find this, the one at the bottom, okay? And take note, this is still the upper percentile, the 95th percentile. So we simply have to look for the 95th percentile of an F distribution with 4 and 2 degrees of freedom, and that's 19.25. And here we can fill this up. We are going to get the reciprocal of 19.25. Okay? And the reciprocal for 19.25 is 0.513. So this is now the value of our 5th percentile of an F distribution with 2 and 4 degrees of freedom. Okay, so if we are going to draw this, we can have this F distribution, and then 0.05 or 5% percentile is somewhere here, so very close to the leftmost part. And this value here is our 0.513. Okay? And the shaded region is 5% of the distribution. So we can actually confirm this in Microsoft Excel. All you need to do is to use the formula F.inverse, okay, wherein you need to input first the probability, in this case 0.05 or 5%, and then degree of freedom 1, in this case 2, and then degree of freedom 2, in this case 4. And once you press enter, you would most likely, or you should get this same value. Okay, that's in Microsoft Excel. So when we test if indeed two variances are equal or not, because we are using the F distribution now, we are doing an F test. Okay? And an F test is most likely going to be two-tailed. Okay? As evidenced by this not equal sign in the alternative hypothesis. So most likely a two-tailed test. Okay? And if your F value is, okay, we have an illustration here. If the F value is greater than your F with this degree of freedom and your 1 minus alpha over 2 percentile, then you are going to reject your null hypothesis. Or if your F value is less than the F value with this degree of freedom and alpha over 2 percentile, then you are going to reject still your null hypothesis. Okay? So, but don't worry, you don't have to be doing this manually anymore because we can use Microsoft Excel for this. So I have here hypothetical samples from 2 populations. So I don't even know what the numbers would mean, but you can put any meaning to these numbers. Maybe these are, let's say, their grades again, or maybe the lengths of their hair, okay? So population A, you have these values. So I think there are 15 of them. And population B, you have these values from your samples. So we are going to test our hypothesis. Our null hypothesis is that the variance of population A is equal to the variance of population B. And for our null alternative hypothesis, we say that their variances are not equal. So in Microsoft Excel, after you've inputted these numbers in 2 columns, you may then go to data and then data analysis, and then choose F-test to sample for variances. And then click on variable 1 and then highlight everything in the first column, including the title, okay, or the label. And then, of course, make sure to check the label here. And then for variable 2, click until there's a cursor and then highlight the second column with the label. And then choose your output range, okay, maybe on the same sheet as where these data are. And then click OK. And you will be given these results. Okay, so what are the important numbers here? You have your F value, that's the ratio of your 2 variances. And then you have the F critical, okay, or the critical region. And then you have the P value. So if we are going to graph this, it's obvious that our F value, 2.72, is already way beyond or greater than our F critical, which is 2.48. Okay? Our decision, therefore, is to reject our null hypothesis. Therefore, there is a significant difference between the population variances of population A and B. And what's the significance? If we are going to look at the p-value, it's highly significant. Okay, this is a statistically highly significant decision. Meaning to say we can trust our decision. Okay, so what's the role of your F-test now? Why am I introducing this to you? Because remember, when we did t-tests in Microsoft Excel last time, we are to choose from 3 possible choices. And usually, what did we choose last time? We chose, or we assumed, especially for 2 sample t-tests, we chose this second one, assuming equal variances. And if you can remember, in your 1 sample t-test where we had a dummy variable which contained all 0, we chose the third one. Okay? But we have been assuming this F-test allows us to know exactly if the variances are equal or not. Okay? So if the difference according to your F-test is significant, the difference in variances, then you will choose a t-test that assumes unequal variances. Okay? So in this scenario, if the difference between variances is significant, you choose the third t-test. But if the differences between the variances according to your F-test is not significant, then you choose the second choice of t-test here. Which leaves us one last question. When do we use this t-test that's paired for 2 samples? You can use this first t-test if you are going to compare before and after. Okay, say for example, you have a sample of children, okay, whom you have administered vitamins to. Okay, and then you are going to check their rate of growth. So maybe on the first column, you have the rate of growth before letting them take the vitamin. And then on the second column of your data, you have the rate of growth after you have let them take the vitamin. Okay? So there's a before and after, and you want to compare the means of these two. Is there really a difference between the means of these two? You use the first t-test, the t-test for paired two sample for means. Okay, that's a before and after test. Okay, so for now, we have done everything for hypothesis testing for at most two populations. In the last module for this particular subject, we are going to talk about hypothesis testing for 3 or more populations.